Today, I will talk about the container orchestration and management. So I'll give you the comparison from the technical view to talk about from the implementation instead of just listing functions of all of the projects. So I'm Hari, and I work for hyper.sh, and I'm a feature maintainer of Kubernetes. So let's begin our talk. The scope of this talk, I will use three typical projects here, which are open source: the Kubernetes from CNCF, and Docker from Docker Corporation, and Mesos from Apache Foundation. So Compose and Swarm will not be included in today's session because those two projects are kind of legacy. So, and on the other hand, the DCOS will not also be included because its scope is much larger than the orchestration and management. So let's begin. So first of all, let's talk about the core idea and architecture about this project. So let's begin from Kubernetes. In my opinion, so Kubernetes is designed to help you to build right things with containers by following its unique concepts and convention. So it's more like a Spring framework in container ecosystem. And its design is quite simple. It was composed by master node and worker nodes. And both of those nodes are composed by several independent binaries. So this has some benefits. For example, we have the ability of modular, transparent, and easy to manage, but also has some disadvantages, like it will be a little bit more complicated to deploy the system. But this problem has been solved and a little better when 1.4 is released, so you have kubeadmin to deploy the cluster. And another philosophy of Kubernetes is that it encourages users to use plugins to do the network and persistent volume stuff. So instead of building something, so it's different. And the whole architecture of Kubernetes, I think, is actually driven by control loops. Let's see why. For example, if you want to create a pod in Kubernetes, so you just send a request to API server, and after that, it will create an object, the pod object in the etcd. And the next step, it does not need to call the scheduler or Kubernetes to do something because scheduler itself is actually an event loop. It keeps running to check if there's a new pod created. So it will try to bind a new pod with a specific node by using its algorithm, scheduler algorithm. So after a pod is binded to the node, it does not need to call the Kubernetes again because Kubernetes itself is just running its own independent control loop to check if there is a new pod bound with me. So if yes, I will fetch the information of that pod to this machine and start all the container inside it. So that's how you can start or create and start a pod. So after your pod has been created, the control manager will be responsible for making sure that everything is okay. For example, the replication controller, it will keep checking your desired number of instances against the real numbers in your cluster. So that is a so-called reconcile process. It's also implemented by a control loop, right? So you can see here that all of the mechanism of the controller is actually following the basic control theory, which uses a feedback loop to decide what to do next. So it is the basic model for all of the controllers in Kubernetes, and of course, for the Swarmkit orchestrator. So let's go to the Docker part. And Docker now has the built-in cluster support for Docker container, which is powered by Swarmkit. And the Swarmkit design is very similar to Kubernetes, which is also composed by a master node and worker node. But all of those nodes, all of the components of those nodes are built into a single binary. That is different from Kubernetes. And on the other hand, it uses a built-in data store. So let's begin with this architecture. When you create a service in Docker, so in the future, Docker will not encourage you to create a single container. It encourages you to create a service. So if you create a service, those requests will be handled by the API layer and then create a service object in its built-in data store. And this data store is actually implemented by Raft protocol together with the memory DB to store your object. So after that, Swarmkit also maintains 4 event loops. So first event loop is the orchestrator, which is very like a replication controller in Kubernetes. So it will create tasks from your just creating new services. And the task is actually a container. For example, I want to start a container. That is the task. And after an orchestrator creates a task, it will keep running the reconcile process to check if there are right number of tasks running in the cluster. So it's pretty much like a replication controller. And the second event loop in Swarmkit is allocator. It's responsible for allocating all side resources, for example, the network to the tasks to containers. So it will call the Docker Network API to assign, for example, the virtual IP, the pod, the IP addresses for container to all of your resources, to all of your services and the tasks. And after your task has been allocated with network, that means it will be ready to do a schedule. The scheduler, which is also an event loop, it will scan all the unassigned tasks and use a node heap to do the scheduler. And it will search the heap to find a base node which meets the requirement of your user's constraints and has lightest workload. So that's how the scheduler algorithm works in Swarmkit. And the constraints are very simple here, just composed by 3 kinds. For example, we need the node in ready status. We need a node with enough resources, and we also need to meet the user requirement, just like what label and label selector can do in Kubernetes. And the last event loop here is dispatcher. So when your task has been assigned to a node, it needs to know how to run the task on the node. So it is the responsibility of the dispatcher. Dispatcher is actually connected to every node by using a long-running gRPC stream. So whenever your task is ready to run, it will send your task information through this stream to the worker node, to the Docker worker node, to the Swarm worker node. And the worker node also sends back heartbeat to say, yes, I'm alive. And the dispatcher will send task to a node. So if we put all of the things together, we'll have a Swarmkit architecture. So we'll see that in every work node, there is also an executor to run your tasks to Docker daemon. So it will use the adapter to translate your information in the task to Docker daemon API. So that's basically how Swarmkit works. So let's go to Mesos. I like to describe Mesos as a distributed system kernel because it's just like treat your cluster as a single computer, right? And it is originally designed to run big data job. And the core idea of Mesos is actually the 2-level scheduling, which is enable the fine-grained resource sharing by mixed running multiple frameworks in your cluster, because you can see here that different frameworks in your cluster actually have different resource usage pattern. So when you mix them together, you will have more possibilities to improve your resource efficiency. That is the original basic idea of Mesos project. The design of Mesos is typical composed by a master, slave, and a zookeeper to a coordination. And since it is using 2-level scheduling, that means every framework in Mesos should have its own scheduler and its corresponding executor to run a task. That also means you need to compare. You cannot compare Mesos to Kubernetes directly. You should compare, for example, Mesos with Marathon with Kubernetes, because all the orchestration and management function actually provided by the up-layer framework, which is Marathon. And Mesos uses containerizer to deal with the container runtime part, and we can talk about it later. So let's see a very good example from Berkeley. Talk about how Mesos works. So Mesos will keep checking all the available resources in your cluster, and it will offer all of the available resources to up-layer framework. So that part is called the so-called resource offer. So it will send resource offer to the frameworks one by one. And the resource offer actually just looks like a profile of your available resource of every node. So it will send this to, for example, the up-layer framework, and the up-layer framework will use its own scheduler to decide which node I will choose. So if it accepts this resource offer, it will send the task to the corresponding slave node. So the slave node will be responsible for launching an executor to run a job, to run a task. Yeah, that's basically how Mesos works. People may be curious that where is the Docker? So actually, before 1.0 release of Mesos, it used a Docker containerizer, which actually implemented by a Mesos Docker executor here. It will generate tasks from your Docker image and run the tasks in executor, actually translate it to a Docker API to call Docker daemon. But after 1.0 Mesos released, actually, it has its own Mesos containerizer, which you can just imagine like a replacement of a Docker daemon. So now, Mesos does not need to rely on Docker daemon because it can do everything the Docker can do. Yeah. So let's reach a checkpoint here. So we can see both Kubernetes and Swarmkit are using event loop driven, and Kubernetes is using etcd, but Docker Swarmkit actually use the built-in data store. And both Kubernetes and Mesos are now can deal with multiple container runtime, and multiple container images, but Docker Swarmkit will stick to Docker daemon. So yeah, that's a checkpoint. And when talking about the building data store, I think there are some benefits and disadvantages. It will be easy to set up. It's super easy to set up. And it has fewer round trips. And it is easier to do some performance tuning. For example, you can build a local index for your building in MemberDB. But there are also some disadvantages, like I think the most important thing is that it is very hard to debug this kind of system. If you want to do a redevelop, you want to change the data store of Swarmkit, well, that's a problem. And another thing I need to mention is that it is not easy to maintain because it is lack of some management API, like backup restore and monitoring. You can just check the etcd administration guide to see, yeah, there are a lot of things missing in Swarmkit's data stores. That's a problem, so you need to make a choice here. The second thing is about the control panel. The control panel is actually how to do orchestration and management. So it's defined when I want to do next through the whole automatic workflow. So there are a lot of important things, but I just want to talk about 5 of them. The most important thing of control panel, I think, is the workload management. It's just like how to manage, for example, a web server with 2 applications. And in Kubernetes, it uses deployment to do that. And in Docker Swarmkit, it uses service. Again, I need to say that Docker will encourage you to use service instead of containers in the future. And for Mesos and Marathon, and it uses an application to do that. And both Kubernetes and Mesos can support the version control of this deployment, but in Docker Swarmkit, it's not supported yet. But it will support in the future, of course. And the Kubernetes deployment is quite interesting and simple. For example, if you create a deployment here, for example, you will get the design number of your deployment and the current number of your deployment. And the up-to-date means how many instances do you have are running latest version. And the available means how many instances are running the right version in your cluster. So it's quite simple. And you can also use the kubectl edit to change the items of this object. That means kubectl will open the editor for you to open the object starting etcd, so you can change the item as you will. And if you save your modification, it will trigger a rolling update automatically. So Kubernetes will kill old instances, start new one, kill one, start new one to do that. Yeah, so that's rolling update. And you can also use set image and scale to change the deployment, of course. And since it has a version control of the deployment, so you can use the rollout command to see the history and use undo command to reset to a specific version. But in Docker Swarmkit, it is quite simple now because this is the philosophy of Swarmkit. They want to keep everything simple, so it just supports some basic control commands like scale and start. But it also supports rolling update. But this update actually, because Docker is using command line for everything, right? So it has to provide you some options, some duplicated option, like you need to have environment add, but you also have environment to remove because it cannot figure out what you want to do during the update. So it is Docker Swarmkit, and in Marathon, it is using application, which is supposed to start, update things, and it is also supposed to rolling update. But please note that the Mesos Marathon actually respects the dependency of your applications. It will rolling update your applications one by one in the right order. So yeah, it's powerful. And it also has version control, and it allows to roll back to a specific version, which name is deployment. So any modification you made to the Mesos Marathon application will generate a new deployment, basically. And the next thing is secret management. So it describes how we can store our encrypted credential data into etcd and then use a container and a pod to consume it. So Kubernetes implemented this by secret volume. So in pod, you can just consume those secret credential data by using, for example, environmental variable or a volume file. It is not supported in Docker Swarmkit yet, but it is under discussion, so I think maybe later. And for Mesos and Marathon, this only supported in DCOS, which store data in Zookeeper and consume the in Marathon. And another similar feature about this is the configuration management, which is described how we can store our configuration data from the file and store it in etcd and consume it later. So in Kubernetes, it is implemented by config map. And in Docker Swarmkit, it is also under discussion. And in Mesos, it is not supported yet in Marathon. The next thing is the auto-scheduling, and it is implemented in Kubernetes by using the horizontal pod autoscaler, and it uses CPU usage as a target resource by default. But The thing I need to mention today is that the Kubernetes actually allows you to do a custom metric. For example, you can specify that I want to use a resource which name is the QPS and the target value is 10. So you need to tell Kubernetes how can it read data, right? So you need to provide a URL to it, and you also need to tell Kubernetes how can it filter out the data from the response. But actually, if you are using things like Prometheus, it will become much simpler because Prometheus and Kubernetes are all belong to the same CF project. So they will share the same metric data structure. So you just need to provide a URL. And the Kubernetes will know how to read metric data from that URL. So I think that's the power of the foundation, right? And in Docker Swarmkit, it's not supported yet, but still under discussion. And in Marathon, this is implemented by a standalone autoscaler. So it will read the internal metric data from Mesos and to decide which one to use as your target value to do the autoscaler, to do the auto-scheduling. So yeah, that's pretty simple. And the last part is the stateful workloads, and it is implemented in Kubernetes by pet state. I think you guys may know it. So in this case, Kubernetes will provide every replica with stable membership and volumes, just like the example I show here is a Cathedral, 2 Cathedral instances. So all of these instances will have their own index, unique index, and with their own specific volume. So if you kill instance or restart instance here, it will start with its own index. So with the same host name, we host the same DNS record, and with its own persistent volume. The persistent volume will never be deleted unless you delete the whole pod or whole deployment. And in Docker Swarmkit, it's not supported, but because Docker does not encourage a user to run the stateful application, it's not its philosophy. And in Mesos and Marathon, it is implemented by the so-called stateful application, which use reserved resource. So if a resource offer has accepted by a stateful application, it will not be sent to other frameworks, even though the instance is deleted. So that's reserved. So that's why you can reuse this part of resource later. And it's the same thing about the persistent volume. It will reuse the existing volume, even though you recreate or restart the instance. And it is using a reservation label to, just like an index, to say, yeah, this persistent volume belongs to me. It's use a label to do that. And the third part is about service discovery and load balance. So basically, this is very important in your system because you need to know how to file your container, how to file your pod. But in Kubernetes, this is all implemented by your IP tables-based solution. So for example, let's begin from the internal traffic. Your internal traffic will reach a portal rule first. And actually, all of those are built on every node in your cluster. And a portal rule is actually a virtual IP and a pod. So this is your portal. And after that, your traffic will be redirected to a group of random mode IP tables. So this is where load balance happens. This group of IP tables will randomly choose a backend rule in your cluster that actually this backend rule will be responsible for pick a real pod to redirect your traffic to a real pod, the IP address of a real pod. So that is how the Kubernetes service works, all based on IP tables. And you can see here the problem because all of the IP tables are created on the node in the cluster. So how can I reach my portal from outside the world, right? So Kubernetes actually provided you a lot of solutions. And basically, the idea is the same. That is, you can assign IP address which can route to any node in a cluster and use that IP address as a portal. So it can be a floating IP, right? It can also be the real IP address of any node, right? So yeah, it all works. And on the other hand, if your Kubernetes is running on OpenStack, AWS, or GCE with the cloud provider, I mean, so you can use an external load balancer. So it will create you an ICE layer load balancer to do the same thing. And there are also a built-in ingress here, which is implemented by Nginx and HyperHQ. So if you use that, just like this example, your request will be firstly proxied by this pod and then redirect to the internal service. So the things next are all the same, just you have the outside portal here. And on the other hand, since Ingress is an L7 solution, so you can do things like SSL on that part. And for this, for name service in Kubernetes, it has a built-in SkyDNS pod to do that. And I think there's nothing special here. But in Docker Swarmkit, I need to say that its solution is much more complicated. So please follow me here. We can begin from the internal traffic. So after you create a service in your Swarmkit cluster, it will create a container sandbox for every service and container. So the sandbox is actually a network namespace. So inside the namespace, it will have IP tables and IPv6 rules configured. So when you send an internal traffic, it will be first translated by internal DNS from its name to a virtual IP. So this virtual IP is also maintained by IP tables, just like what Kubernetes did. And after that, it will these IP tables rules will redirect your request to the IPv6 module, which knows how many containers they have for a specific service. So this is where the balance happens, and it will pick a backend container for you to do the redirection. So it has to use the user-defined overlay network to do that, to reach container on either node. So this is the internal traffic, but for the outside traffic, for the outside access, the Docker Swarmkit actually has a totally independent solution, which name is routing mesh. So if you send a request from the outside world, you should reach a port mapping rule on the node. And after the port mapping rule, it will send a request to a so-called ingress sandbox. And this sandbox exists on every node in your cluster. So inside of that sandbox, there is a group of IP tables to redirect your request to the IPv6 module. And this IPv6 module also knows how many containers they have for a specific service. So it will do the balance part just like internal traffic before, but it has to use an ingress overlay network here because it also needs to know how to connect to each container running on any nodes in a cluster. So you can see here, the Docker Swarmkit has to maintain at least 2 overlay networks here, the ingress one and the user-defined one, and they had to maintain 2 kinds of sandbox here, one for ingress and one for the user-created service and container. So that's the load balance part in Docker Swarmkit, and for name service, it uses embedded DNS server here. So in Mesos Marathon, however, it is much easier because it is using a HA proxy-based load balancer here, so everything just happens on HA proxy side. And for the external case, it's just the same question: how can you expose this HA proxy to outside world? So basically, so in most cases, a public IP will be enough. And for name service, Marathon is using a Mesos building DNS to do that, so it's quite simple. Let's reach a checkpoint here. And in Kubernetes, both in Kubernetes and Swarmkit, they are all using IP table-based virtual IP as a portal. And but in the load balancer part, there's a difference. Kubernetes is still using the IP tables-based solution, the running mode, I mean, and but in Docker Swarmkit, it is using the IPv6 to do load balance. And for the external service, external access, the Kubernetes provides you with several ways, which actually allows you to reach IP address of a node first. And in Docker Swarmkit, however, it is using a so-called routing mesh, which requires the extra ingress overlay network for you to do. And in Mesos Marathon, it is using HA proxy, so things become much simple. And Kubernetes watched its etcd to update all of the IP table rules on the node, which is done by Kubernetes proxy. But in Docker Swarmkit, it is using underlayer gossip protocol to advocate the information about the network and the rules. So it does not watch its wrapped building data store. So that's the difference. And in Mesos Marathon, it is using a standalone updater, use the HA proxy template to do that. So let's go to the scheduling part. And in this part, I think I have lots of things to say because Kubernetes actually use pod as this scheduling unit. But it's unique, but why? So I like to give you this example because a lot of people want to run a Java application, right? You need to package your WAR file to a Tomcat. So in Kubernetes, you can just define this WAR file, this WAR container as a init container. So it will be started before all of your user containers, and you can ask it in a command to copy your WAR file to a shared volume. And after that container exit, your user container, which is the Tomcat, can just load its WAR file from the shared volume and to start your application. So you don't need to package your WAR file with your Tomcat, and you don't need to use the persistent volume to store the WAR file to load it later. Yeah, so that's how pod works. It allows you to do something which is the so-called container design pattern to decouple your containers, right? Yeah, so that's the power of pod, and that's why Kubernetes uses it. It actually lesson learned from Borg. And Kubernetes also supports multi-scheduler, so you can specify which scheduler I want to use for this pod by just adding annotation in your YAML, in config YAML. And it also supports the QS tiers, which actually the core idea of a Borg. The core idea of a Borg is that it allows you to mix up different applications with different priorities. So you can do resource preemption here. So that's one of the core ideas of Borg. And it is the same with the Kubernetes. So it has 3 kinds of priority, actually. For example, here is a bustable pod, which actually you can see request 64 memory MB memory, but its limit is 128 MB. So it actually over-committed 64 MB memory in this case. That also means this pod can be killed whenever this node is under memory pressure. Yeah, so that's the QoS tires. And actually, more and more Borg features are introduced into schedulers. For example, the equivalency cache, which is what I'm doing today, and the pod level resource boundary, which also the core idea of the container in Google. So yeah, that's our all interesting features, which can make it possible for you to run your workloads in much larger scale cluster. And in Docker Swarmkit, it's scheduled quite simple, very simple, as I had described before. And it is using the very simple node heap to choose the best node which meets your requirements, the constraint requirement, and of course, choose the nodes with the lightest workloads. So it's quite simple, and it does not support multi-scheduler or QoS tires yet. But I think in the future, Swarmkit scheduler will become much more powerful because it is keep borrowing idea from Mesos and Kubernetes, right? And I think it's a good news. And for Mesos and Marathon, actually, I think scheduler is the best part of Mesos. And it's supposed multi-scheduler, of course, because it is designed to run multi-framework, right? And for the strategy part, it is using the 2-level scheduling, which is the killing weapon of Mesos, because it has been proven in the Twitter scale production cluster, right? And it also allows you to do fine-grained resource sharing, which can improve resource efficiency, just like what you did with Borg. And for QoS tires, of course, it is supported, and actually it supports much more features in scheduler part than Kubernetes and Swarmkit, like task conviction and data locality, maximum fairness, priority, and offer drift and delay scheduling. So those features are all the secret why Mesos can support so many nodes in the clusters. Yeah, so that is what Kubernetes is catching up. And another point today is that Mesos is only project here which can help you to run the big data workloads. Both Kubernetes and Docker Swarmkit cannot do it very well. And so let's reach a summary part. And in our case, our user case is HyperHQ, which is described as a Docker done in the right way. So in our philosophy, we're trying to wrap our cloud container as a single container. For example, you can just run hyper-run to start a container, and you can use link. You can attach a FIP to that container directly. So it looks very much like Docker, right? But actually, HyperHQ is powered by Kubernetes. And people in Hyper also maintains a lot of Kubernetes feature. So let's see why. So in our user case, we think that the extensibility really matters. And in HyperHQ, we are using the so-called Hypernative project to do everything. So it is actually using hypercontainer, which is based on hypervisor container as a container runtime. So it is implemented by the container runtime interface of Kubernetes. And we have our multi-tenant network based on Neutron. So it's different from container network. And we have also custom standard plugin, use safe backend to support our persistent water volume. And we use our customized HA proxy-based service for a multi-tenant service in our cluster. So in all of these cases, I think it's very hard for me to imagine how can I implement those features in, for example, Docker Swarmkit or Mesos, because it will be much harder since Kubernetes has a lot of plugins and its design is decoupled for us to do that. But it's not the case in Mesos and Docker Swarmkit. So I think the Kubernetes is truly extensible and configurable if you want to do things like this. So here's some summary, just my personal idea. So if you are an individual or organization trying to find something that works and is simple, friendly, and just works, so I think Docker Swarmkit is really good. But if you are a corporation which has a Twitter scale cluster to manage, for example, 10,000 nodes, right? Or you are prepared to run some big data workloads like Spark, Hadoop, or Storm, you need to Mesos, of course. And but if you just like me, just like Hyper, you just need an infrastructure layer, and you want to build your own system on top of it in the right way. By saying in the right way, I mean you want your system to be maintainable, to easy to do refactoring and robust. So I think that in that case, Kubernetes is the best choice because it is designed to allow you to run things, to build things on top of it. Well, this is the end of my talk. So do anyone have any questions? Yeah, please.
So why does Linux use Borg?
Oh, sorry, what?
Why does Kubernetes use some of the OpenStack projects like Neutron?
Oh, yeah, because Kubernetes is using hypervisor-based container. So it cannot use the solutions which are designed for Linux containers. It has to use the network for virtual machine and the persistent volume for virtual machine. So that's why we use OpenStack components. Yeah. Oh, yes, please. Please first.
Does Kubernetes offer persistent storage applications?
Oh, yes. We use standard volume, which is based on safe. So it will attach a safe RBD object directly into your hyper container. So that's for persistent volume. You can claim you are using persistent volume, and that's also done by standard volume. Yeah. Yeah, please. For now, we don't have very complicated network policy because we are just what we have done is just to implement a layer 2 isolation. That is all for our network for now. But in the future, we will have some, for example, the secure policy to, for example, to limit your batteries or to change the batteries. But for now, we don't have that. We do not have it yet. Yeah. Hypercontainer is implemented by hypervisor to replace the isolation layer of container, but it uses Docker image. So just replace the group namespace by using hypervisor, but we still use Docker image, and we have our own kernel running in it, which will be very small and very quick. So you can start up a hypercontainer in just within I think 1 second. It's very quick. So it's basically using hypervisor technology, but it's not like a full-blown virtual machine. It's just like a tiny virtual machine. And we use this hypercontainer as a pod. So we run containers inside, but it's actually as a physical boundary of the pod in Kubernetes. Yeah. Just like sandbox. Kubernetes has a concept of sandbox. It is actually the pod. So we use hypervisor and sandbox, right?
So does that mean that each container is isolated from the others using essentially virtual machine?
Actually, you should say in Kubernetes way, you should say every pod are isolated. Yeah, not every container. Every container has mount namespace, but their resource limitation is not guaranteed. Yeah. So within a pod is not guaranteed. Yeah. Okay. So if there are no more questions, I think this is the end of my. More question? No. This is the end of my talk. So you can find me through my email if you have any question about the hypervisor-based container, and you can find my GitHub ID and Twitter, so you can connect to me very easily. Thank you.